All right, let's dive in. Today, we're going to tackle a topic that I know can look super intimidating, rational expressions. But I promise you, by the end of this, you're going to see it's all about using a few simple rules you already know. Let's do this. Okay, take a look at this thing. I know, right? It looks like a complete and utter nightmare. You've got variables, exponents, polynomials stacked on top of polynomials. Your first instinct is probably to just close the textbook and walk away. But hang on, stick with me for a minute. Because what if I told you that underneath all that mess, the core idea is something you've been doing for years? Seriously, getting this one simple concept is the key to unlocking the whole thing.
Remember this? Just simplifying a basic fraction. You find what they have in common, in this case it's 12, and you just cancel it out from the top and the bottom. So 12 over 60 becomes a much nicer, much friendlier 1 over 5. Simple, right? You've done this a million times.
Now check this out. That fancy algebraic fraction on the right, the one that looks so scary, it's the exact same process as the simple one on the left. You're just canceling out common factors. You know, like these little groups of x plus 2, instead of just numbers. That's it. That's the whole secret. Okay, before we start multiplying or dividing anything, we have got to talk about the one absolute unbreakable rule of rational expressions. This is the one thing you can never, ever, ever forget. So what even is a rational expression? Well, by definition, it's just a fraction where the top and bottom are polynomials. You know, stuff like x squared plus 2x. But look at that last part, the fine print. The denominator, q, cannot equal 0. This is so crucial because, as we all know, you just can't divide by 0. And this is why. If you try to plug in a number for x that makes that bottom part 0, boom! The whole expression becomes undefined. It's like the universe of math just short circuits. It can't compute. And this is exactly why we have to find our restrictions before we do anything else. So how do we stop the universe from breaking? It's actually super simple. You just take the entire denominator, set it equal to 0, and solve for x. Whatever answers you get, those are the values that x is not allowed to be. So for this one, x can't be 1 and it can't be -2. Those are our restrictions. Easy enough? All right, with the golden rule firmly in place, we are ready for the main event. Let's talk about multiplication. And to make this as easy as possible, we're just going to use a simple 3-step mantra. Here it is. Just burn this into your brain. Factor, cancel, multiply. That's it. This is your game plan for every single multiplication problem. First, you break everything down. Second, you look for twins on the top and bottom and cancel them out. And third, you just multiply whatever's left. Okay, enough talk. Let's put our mantra to the test with this beast of a problem right here. I know it looks like a mess, but we've got our 3 simple steps to guide us through it. First things first, step 1, factor everything. We're breaking down each of those polynomials into their smallest possible parts, their binomial factors. And why are we doing this? Well, it's kind of like finding the DNA of the expression. It reveals all the common pieces that might be hiding inside, and that's the key to making this whole thing simpler. And now for my favorite part, the really satisfying part. Step 2, cancel. We just scan through and look for matching factors in the numerator and the denominator. So we see an x plus 1 up top, and on the bottom, gone. We see an x minus 2 on the top and bottom, they cancel out too. So satisfying. And finally, the home stretch. Step 3, multiply what's left. All we have to do is multiply the stuff that survived in the numerators and multiply the stuff that survived in the denominators. And boom, there it is, our clean, simplified answer. Way better than what we started with, right? Okay, so you've totally got multiplication down. What about division? Well, I have some fantastic news for you. If you can multiply, you can 100% divide. There's just one tiny little extra step you have to do right at the beginning. Look how this builds. For division, all you have to do is take that second fraction and flip it upside down. You know, find its reciprocal. Then you change the division sign to a multiplication sign. And after that one little flip, guess what? It's the exact same factor, cancel, multiply process we just mastered. All right, let's see this thing in action. Here's a typical division problem. The very first thing our eye should go to is that division sign. That's our cue. That tells us we've got to do the flip. So we take that second fraction, we invert it, and we change the problem from division to multiplication. And just like that, we are on familiar ground. We know exactly what to do from here. So we just follow our mantra. We factor all the polynomials. And then, wait a minute, would you look at that? An x plus 8 cancels, an x minus 8 cancels, and an x minus 3 cancels. Literally everything cancels out, leaving us with just the number 1. I mean, it doesn't get any simpler than that. Okay, so we know how to do all this. We've got the steps down. But the big question that's always in the back of your mind is, why, right? When am I ever going to use this stuff in the real world? Well, let's look at a classic example. Imagine this scenario. You've got a passenger train and a freight train. They're traveling different distances at different speeds. We can lay out all this info in a nice, neat table. And we all know the classic formula, right? Distance equals rate times time. Well, if you just move that around a little bit, you get time equals distance divided by rate.
Now here's the kicker. The problem tells us that the travel time for both trains is exactly the same. That's our key. That's our aha moment. So we can literally set the time expression for the passenger train equal to the time expression for the freight train. And just like that, we've built a rational equation that actually models a real-world situation.
And how do we solve this thing? You guessed it. We use the exact same principles we've been practicing. Yeah, there are a few extra steps, like finding a common denominator, but the core logic is the same. We work through the algebra, we solve for x, and we find that the speed of the freight train is a real, tangible number. 45 miles per hour. See? This isn't just abstract math. It's a powerful tool for finding real answers. So if there's one thing to take away from all this, it's that so many problems that look impossibly complex are really just built from simple, logical rules. We saw how a scary-looking expression was just a simple fraction in disguise. And it really makes you wonder, doesn't it? What other complex problems out there are just simple rules waiting for us to figure them out?